So in this video, we are now going to look at one more relationship with indices. And this is as far as we'll go at this stage. There are a couple more that arise, but for the time being, these are the only ones we're going to work through. And after this video, I'll have a couple of videos showing examples of how to actually work with indices. Now, we're going to look at the effect of taking the power of a power, right? So let's say I had 2 squared to the power of 2. Well, I'm going to simplify what's in this bracket first. And what's 2 squared? Well, that's just 2 times 2. So I'm going to get 4 all squared. Now, what's 4 all squared? That's just 4 times 4. So this thing equals 4 times 4, which equals 16. Okay. The actual maths there hopefully wasn't too bad, the actual arithmetic. But, well, let's just decompose this line of working a little bit. Because we started off with some base 2. So in the end, I want to kind of leave these two answers we got in terms of just 2. So this thing here, 4 times 4, well, we know that 2 times 2 is 4. So that's like saying this one here is 2 times 2. And that's multiplied by another 2 times 2. All right, well, what do we have here? We have 4 2's all multiplying by themselves. And what we learnt in our previous couple of videos is we can express this in a shorthand way as just 2 to the power of 4. And because this is equal to 16, that means we can also write 16 as 2 to the power of 4. Now let's look at what actually happened. I'm not gonna give it to you straight away, but have a look at how this 4 related to maybe these two powers here. But just pause with that thought, and we're gonna work through one more example and see if we can come up with a general formula once again. Now let's look at the effect of. Okay, let's try another example. So let's do 4 squared to the power of 3. All right, well, what's 4 squared? That's just 16, isn't it? So we'll get 16 cubed. And 16 cubed is like writing 16 times 16 times 16, right? Now, we're going to get a relatively big, like a bigger number, I guess, than the one we've been working through. But like we did in the last couple of questions, let's express each of these as a power, as a base of 4. Well, this is like saying this one is just 4 times 4. This one is like saying 4 times 4. And this one as well is like saying 4 lots of 4. So what do we have here? Well, we had 1, 2, 3, 4, 5, 6 lots, with 6 4's all multiplying by each other. And what we know from indices is that if we imagine each of these to be to the power of 1, when we multiply the same base, two numbers of the same base, we add their powers. So this is just like saying 1 plus 1 plus 1 plus 1 plus 1 plus 1, which gives us 4 to the power of 6. Now, between these two examples, I should have done these next to each other really, but that's okay. Hopefully you can all see that. But between each of these examples, now I'm just going to zoom in. What do we observe between the final power in the answer and these two powers here, as well as this one and these two powers here? Well, when we took a power of a power, to get the answer, to get the final power here, well, this thing is just a product of these two, isn't it? Because 2 lots of 3 is 6. And the same thing before, we had 4, which can be made out of taking 2 times 2. So when we have some indice all squared, so this entire, I've written brackets here on purpose because I'm finding this first and then squaring the answer, I get some answer which has the same base and a power which is the product of the power of the power. So once again, we'll write a general equation. A general formula for powers of powers. Sorry about that. Oh, Jesus. Okay, let's do that again. So general formula of powers of powers. Well, what did we just observe? We observed that some base a to the power of m, when all of this inside the brackets was raised to another power, n, this was the same effect of just leaving our base a and taking a product of these two values here. So that's like the same as saying a times m lots of n. And this thing here is our general formula for dealing with powers of a power. And guys, with all the examples I've given you in the last 3 videos, I encourage you, play around with different numbers. Don't just take my word for it. Maths is about your own interactions with this as well. Grab your calculator, mess around with these types of things. I've worked with very small numbers on purpose here, just so you can kind of do the calculations in your head. So it's not too mentally straining, but try even on your own, like working through higher powers and see if you're still observing these types of patterns. You know, you can in your own time tell me what, 5 to the power of 6 all squared gives me, and then use your indice kind of laws that we've come up with. Have a go at this. Come up with an expression of this to the base 5, and then put it into your calculator. Write it all in a different amount of ways, and you'll see that it all gives you the same answer. Play around with this in your own time for each of our 3 formulas. For this one that we've just derived here, as well as the other ones for multiplication and division of indices. Try this with a bunch of different powers, and you can even go higher. I mean, as high as your calculator will allow, but mess around with this with these things, guys. It's all about your own interactions with these mathematical concepts. Don't just take what I'm saying and take it as gospel. Try it out for higher powers. Maybe it doesn't work for powers above, 3, or 4, which I worked through in these last few videos. Try it for even higher ones, and you'll see that the laws of indices that we've derived hold true for all of these. But give it a go for yourselves. Sorry for the tiny rant at the end, but I'm really just trying to encourage you to have a go at doing your own self-study with these. Try to spark your curiosity by working through, more complex examples. Try using higher powers and see what happens. Try to discover it for yourselves as well as watching these videos. But we'll be going through some more examples in some later videos, and I'll see you there.